All right, we're recording now. Good morning again, everybody. Especially for those who just came in, sana nakikita niyo yung screen ko. If you can't, just let me know para ma-restart ko siya. Because now I'll be doing a free-flowing lecture again. I don't have the notes for this yet, pero most of the discussions I'll do today is based on Silton and Section 2.2. I have uploaded an excerpt to their textbook dun sa ating Canvas page. So kindly download it. Yung lecture last time, isulat ko na lang siya in a typewritten form and I'll upload it all over the reading break. Yun nga pala, congrats. We're halfway through the semester and reading break na. Tama nga ba? Next week na yung reading break, ano? So looking forward to it. Uh, Parang nung ano nga, may mga times na nagsusulat ako ng isang proposal or nagsusulat ako ng isang report. Parang akala ko ay ano na, second sem na, yung pala first sem pa lang ano. So akala ko sa dami na nangyari this past few months, parang ano na, kalahating taon na yung nagdaan. Or actually, yeah, parang nasa second sem na tayo, patapos na yung acad year. Pero anyway, so how is your problem set going? May progress ba? Ano nangyayari? Or sir, bakit ka naman nagtatanong ng ganyan, eh, ano pa yon? Sa Friday pa yung deadline ano, tama ba sa Friday? So, saka na po namin gagawin, power of cramming. Okay. Now, sometimes it works because for me personally, hindi ako yung magaling gumawa ng maaga sa or mas maaga kaysa sa deadline. Um, Parang ano parang mas ano ako, mas productive ako 'pag malapit na yung deadline. Parang ano, may natutunan nga ako over the graduate school workshop, yung tinatawag na Pareto Principle. I don't know if you have heard of it. Dun sa mga OR dyan, probably you already heard of it. The Pareto Principle says that we are, or 80% of our outputs are obtained in 20% of our time. So yung 80-20 rule. So 80% ng ating most significant achievements ay nakukuha natin dun sa 20% ng ating oras. Meaning dun sa parang power hour nung yung parang yung power hour natin, dun natin nakukuha yung mga pinakamalalaking outputs natin. And for me, my power hour is probably hours before the deadline, all right? So, hindi ko alam kung effective sa inyo yun, pero if that's effective for you, then magkakasundo-sundo tayo and good for you. I won't judge you if you'll be cramming. Pero kung hindi naman yun yung appropriate sa inyo, so do things ahead of time, all right? Okay, so let's just do a quick review of what we did last time. So I think last meeting we started to we derived the heat equation, or we at least tried to understand how it came about, right? And we learned that the heat equation is basically based on the observations by sino nga yung nag-observe nito? I think it was, kalimutan ko kagad yung pangalan. It was Fourier, right? Who is really very ahead of his time, ano? Kasi si Fourier din yung nagsabi na kahit anong function ay kaya nating isulat as a sum of sines and cosines. And people laugh at him during that time to a point na parang dinidiscriminate siya ng kanilang Academy of Science and Technology because they can't believe what Fourier claimed, that all functions can be written as a superposition of sines and cosines, and yet in the 19th century, or I think at least in the 20th century, gamit na gamit yung Fourier's method, right? The Fourier series expansion, which is basically writing continuous functions or smooth functions as sums of sines and cosines. Pero nung panahon niya, parang pinagtatawanan siya nun. And yeah, the luminary Fourier was from three observations, he was able to give us what our model for the propagation of heat, or how temperature behaves in a free flowing medium. Ano? So which is basically later was confirmed by experimental thermodynamics and statistical thermodynamics na, yeah, totoo yung sinabi ni Fourier. And the result of his observations is what we call, yun yung sinasabi natin na heat equation, which basically is a second order partial differential equation that tells us how temperature behaves, right, in a certain medium. Sabi natin kapag ka ang medium natin ay isang very thin rod, okay? So if you have a rod from 0 to L, right? The temperature at any point, or the function that represents the temperature at any point x in this rod at any time t greater than 0, right? Follows the following partial differential equation. So ito yung governing law dun sa temperature dito sa loob ng rod neto at any specific time. So basically, sabi ni Fourier or galing sa observation ni Fourier, if you use the temperature, so uxt is the temperature at the point x. So at the point x in space, which is basically a number from, say, the closed interval 0L, at the time t greater than 0, follows the following governing principle. Galing nga kay Fourier, partial derivative ni u with respect to t, evaluated at xt, or maybe it's better to write it this way, d dt of uxt I equals d, then second partial derivative with respect to x of uxt, all right? And this is true for all x's in 0L, in the open interval 0L and t greater than 0. So ito yung governing principle or the governing equation for the propagation of heat. And any function that satisfies this differential equation can be thought of as a characterization of the propagation of heat. Okay? And ang tawag natin sa kanila ay mga harmonic functions. Pwede ko ba siyang tawaging harmonic functions? Time varying harmonic functions. Pero wag na lang natin gamitin yung harmonic. Kasi yung harmonic functions usually ay reserved para sa 0 equals the second partial derivative. So let's just call them temperature function or solutions of the heat equation. All right? And then dun sa mga nag 152 na partial differential equations, Math 152, or those who are taking Math 151, probably you know now that hindi unique yung solution dito sa PDE na to kung meron man. Because you've learned that kung ilan yung order, kung sa ODE, kung ilan yung order, kung ano yung order ng ODE, ganun karami yung undetermined constants, right? Laging dun sa solution, sa general solution, meron kang C1, C2, C3, which represents arbitrary constants. Now, to get a unique solution, ang ginagawa natin dati, nagbibigay tayo ng initial o kaya boundary conditions dun sa ating ODE that is the same number as the order, all right? Ngayon, meron tayong order 2 spatial derivative, meron tayong first order temporal derivative, so meron tayong tatlong conditions na kailangan i-impose para makakuha ng isang unique solution. And they will be our boundary and initial conditions. Okay? Now, our boundary conditions tell us how the temperature function behaves at the two endpoints of our rod. Okay? Masyadong pinadali natin yung characterization o yung discussion kasi one dimension na lamang yung kinuha nating object. So yung boundary condition niya would be that the behavior of the temperature at the left endpoint x equals 0 and at the right endpoint x equals L over all time values. Okay? So kaya for instance here, pwedeng sabihin ko yung left boundary condition ay u of 0, t. Ito yung nasa kaliwa. All right? Tapos let's assume we know this, right? And this is basically the temperature at x equals 0 for all time values. So this is basically just a function of t. All right? So tawagin natin itong g of t. Okay? So parang siya lang. Yung function value ni u sa x equals 0 for all eternity, right? For all time values. And then we also have a boundary condition corresponding to the right endpoint. So this would be the value of the temperature function u at x equals capital L, the right endpoint, and for all time values t. Then this will just be a function of time, so let's just call it h of t. Okay, and collectively, these two guys are what we call the boundary conditions. And then lastly, we want to have what we call an initial condition. Kasi etong dalawang conditions na to will just make the solution unique with respect to the spatial variable. Kasi order 2 yung ating spatial variable, so yung boundary conditions will give us a function or a solution for all for the spatial domain. Pero meron pa tayong temporal derivative dito, so ibig sabihin kailangan pa natin ng isang condition to get a unique solution to the problem, right? Kailangan naman natin isang condition in time. And usually what we consider is the what we call the initial condition, or what is the value of the temperature at all points in the rod when T is equal to 0. Kaya siya initial. Ano yung initial temperature profile ng ating domain o ng ating space of interest, right? Let's denote this by the function f. So this will be the value of u at all x's between 0 to L at time t equals 0, tawagin natin tong little f of x. So ito naman yung initial condition. And then as a quick example, all right, so kung nag-take kayo ng 152, you will learn some methods on how to solve this forward problem. Meaning the forward problem is, we know the governing principle, which is the heat equation you see over here. Oh, by the way, here, capital D is just a constant, positive constant, all right? Na binibigay, depende dun sa medium, right? Nandiyan na, nakasama na dyan yung specific heat, other properties of the medium like heat conductivity, the density of the medium, etc. So inassume lang natin silang lahat to be constants at we put them together into the constant D. All right. Now, if you took a PDE course, then you would have learned methods on how to solve this forward problem. So we know the governing principle, and you can treat the boundary and the initial conditions to be the input to the problem. Okay? So tapos, mako-compute mo si function u. For instance, I gave you an example of a solution to this heat equation last time into a homework. So parang kaninang madaling araw nakapag-check na ako ng 4 na nag-submit nitong homework nito, and they all got a perfect score. So basically, for instance, si u of xt, which is 10 e to the negative 4t times sine 2x, is a solution of the heat equation over the rod extending from 0 to pi. Now, initial condition niya, 0 yung temperature dun sa boundaries all throughout the time domain. And the initial condition is that u of x0 equals 10 sine 2x. So basically, parang sinasabi nito na, okay. So at the beginning, all throughout time, 0 yung temperature dito sa magkabilang dulo. Tapos initially, alam ko yung temperature dito sa interior ng rod to be satisfied sa pi over 2 dito sa gitna. So x equals pi over 2, ang temperature niya ay 10 sine pi. Tama ba? Ano ang sine pi? Ang sine pi ay, hold on, parang balik na. Pi over 2. Yeah, sine pi. Ano ang sine pi? Sine pi is 0? Tama ba? Yeah. So ibig sabihin, 0 rin yung temperature dun sa gitna. Pero sa pi over 4, ang temperature niya ay positive 10. Sa 3 pi over 4, ang temperature niya ay negative 10. Yun yung nangyari sa initial time. So parang siya yung data dun sa ating problem. Alam mo yung temperature dun sa boundary, alam natin yung initial temperature dun sa interior, tapos following the observations of Fourier, dapat pala yung temperature dito sa rod will always follow the equation 10 e to the negative 40 times sine 2x. All right? So, yun yung maging sagot dun sa forward problem. And you will see that what will happen when napaka-powerful ng observation natin dito kasi we know the function that is followed by the temperature on the rod for all eternity and for the entire rod, Now, we know that, ito yung itsura ng equation. Alam ko na kapag ka ganun yung initial conditions, 0 yung temperature sa boundary, tapos 10 sine 2x yung initial temperature in the domain. Ibig sabihin, in the long run, yung temperature nito ay mag-approach lamang ng 0. Right? Kasi ito yung function eh. Kunin mo yung limit as t approaches 0, ang limit ay equal kay 0. So in the absence of a heat source, kasi ito ay laging 0, ito ay laging 0, yung 10 sine 2x na temperature doon sa loob ng rod will eventually decay to 0 throughout time, which makes sense, right? Kasi ang baba naman itong 10 sine 2x, naglalaro lang to sa negative 10 to 10 degrees. Tapos wala na tayong heat source. 0 laging temperature sa magkabilang dulo. So ibig sabihin, it's understandable that throughout time, okay, for large enough T, magiging palapit ng palapit sa 0 yung temperature dito sa ating rod. An interesting question, which is sort of an inverse problem, is ano kaya dapat, halimbawa meron akong gustong temperature. Halimbawa gusto kong temperature dun sa loob ng rod ay mag-stabilize say sa 25 degrees Celsius, right? Or ang value niya ay maging 25. Question is, can I attain this? All right. Now, by only manipulating the boundary conditions, for instance, halimbawa, ito ay one-dimensional air conditioning system. All right. So, nakaya kong kontrolin yung temperature nitong dalawa. So, parang sila ay mga point aircons, ano? So, ibig sabihin, ano dapat yung boundary conditions? So what should be my function g and h? So dapat ito ay u of 0t equals g of t and u of lt equals h of t. What should be the functions g and h such that the solution of the heat equation will stabilize to 25 in the long run? So alam ko yung intended output. The intended temperature is the constant temperature 25. Now the problem is, how can I achieve this? I can achieve this by manipulating the inputs. And what type of input? First, basically, parang it physically makes sense that we will have control over the boundary conditions. All right? Kasi pwede mo siyang tingnan na halimbawa, point source, heat source, or para siyang cooling source, right? So ano yung function G at H? Dapat na maging left at saka right temperature behavior para mag-stabilize sa 25 yung temperature. Okay? Pwede ring isama yung initial condition into the play as a part of the degrees of freedom into your inverse problem. Pero mas maganda na ito ay hindi nating isama as part of the degrees of freedom kasi pwede natin itong tingnan as physically, meron na talagang ambient temperature yung ating rod, right? So kaya siguro yung initial condition, pwedeng hindi na natin siya pakalaman, given yung initial condition sa problem, dun sa inverse problem, ang hinahanap na lang natin ay yung boundary conditions. Okay? Now, but before we go into solving such interesting inverse problems, tingnan na muna natin yung forward solution. Okay? Now, I will not be teaching you how to solve this symbolically kasi ang point naman ay pag-aaralan natin to as a stepping stone in order to get a solution to the inverse problem. And this is basically a differential operator. This is another differential operator. So basically the solution or the actual operator that gives us the behavior of the heat equation is linear in nature. So ibig sabihin yung etong PDE na to kaya kong i-reduce into a linear system. And I want to look at the linear system kasi yung linear system yung mas madaling paglaruan para dun sa inverse problem. Okay? So kaya hindi ko kayo tuturuan paano to i-solve analytically. So meaning, unfortunately, hindi nyo matututunan from me kung paano nagsimula dito sa governing equation at saka sa boundary at initial conditions, paano nakuha yung u na 10e to the negative 40 sine 2x. That's for Math 152. Pero mas gusto ko kasi ano yung numerical solution dito sa ating ODE. So halimbawa, nag-start ako dito, alright? Paano ko siya masosolve numerically? So meaning how do I transform this into a linear system that a machine can understand? Okay? So ginawa na natin to in the convolution problem last time na nag-discretize tayo ng integral because there we are using the integral operator. This time we have a differential operators, or actually we have differential operators here, temporal and spatial. So titingnan natin yung tinatawag natin na finite difference approaches. So finite differences. So dun sa mga nag-174 na last year, you already seen this, yung paano natin ina-approximate yung derivatives using backward and forward formulas. So for those of you who haven't taken 174 yet, eto, parang spoiler to dun sa gagawin nyo sa 174. How do we discretize or how do we approximate derivatives using computers, right? Kasi meron tayong dalawang klaseng derivatives dito. Meron tayong first order derivative with respect to time, and then we have second order derivative with respect to space. Okay, and that's what we'll look at today. We'll try to build up a discretized version of the governing law in parallel to what we did to the convolution problem in the first section. Okay. Okay, so how do we do this? Okay, so una, kailangan kong i-discretize parehas yung space at saka time variable, right? So remember, our space domain or our spatial domain is the closed interval 0 to L. Pero hindi naman kayang gawin ni computer yung computation sa lahat ng x's na nasa closed interval 0 L because there are infinitely many x's over that interval, and that interval is a compact set, right? Dikit-dikit, masyado yung mga x's dyan. So from 0, sino yung susunod na element? 0.000000001? No, kasi meron pang 0.0000000000001 and so on. Napaka-compact niya. Hindi natin alam kung sino yung susunod na number kay 0, right? So additional problem pa yon aside from the infinitude of the elements of the closed interval. So ang gagawin natin, pipili lang tayo ng mga representative x's over the interval 0 to L. Tapos ganun din yung gagawin natin in the time domain. So we will create a mesh of points. So ito yung first step dun sa ating discretization. Hatiin natin yung space and time domain into a discrete set of points. Okay? So let's start with the spatial variable first. So we will take delta x to be equal to L over m plus 1. So here basically we will reduce the interval 0 to L into how many? M plus 2 points. And the time domain so let's just say we are working on the time domain 0 to capital T, all right? So meron kang terminal time, capital T. Then sabihin natin, sige, hatiin ko yung time domain ko into n plus 2 or big N plus 2 points. Ibig sabihin, ino-observe na lang natin yung temperature in capital M plus 2 points dun sa closed interval 0L at saka N plus 2 moments in time. Okay? And then I will assume that my discretization would be equally spaced. So, ibig sabihin dun sa along the X domain, dun sa spatial variable, ang gagawin kong increment ay capital L over M plus 1 so that si x sub 0 ay C0, yung left endpoint. Si x sub 1 ay equal kay L over M plus 1. Kasi nga ang common increment natin ay L over M plus 1. So from x sub 0, magdadagdag lang ako ng delta x to get to the next x value. And then I'll do the same to get to the third x value. So we'll have 2L over M plus 1. So in general, if I am on the ith x value, I will be at I times L over M plus 1, okay? All the way up to x sub capital M plus 1, which will be equal to L, all right? So ito yung mga M plus 2 na representative points doon sa ating space domain, all right? So that is in general, yung x sub I ay equal kay I delta x. I going from 0 until n plus 1. Okay? And then I'll do the same thing for the time domain. Okay? So I will take delta t. This time, ang haba ng ating time ating observation time ay 0 to capital T. So it's going to be t units in total. So t minutes or t seconds divided by n plus 1. So that the first time value is the initial time 0. And then t1 will be t0 plus delta t. So that will just be t over n plus 1. T2 will be capital T times 2 over n plus 1. So in general, T sub j will be j, j capital T over n plus 1. And this is equal to, this is also equal to j delta T, all the way up to T sub capital N plus 1, which will just be the terminal time big T. Okay? So ito naman yung observation natin, observation time moments natin. So ngayon, na malalaman na lang natin ano yung temperature sa bawat x sub I sa lahat ng t sub j values. So hindi na natin ma-observe yung temperature sa arbitrary point in space and point in time. So malalaman na lang natin yung temperature at specific points in space na kasama dun sa ating discretization mesh at particular moments in time na nandun sa ating time discretization o dun sa ating time mesh. Okay? Kasi ito ngayon, maintindihan na to ng computers. Alright? Kasi nga, finite na lamang yung observation points at observation moments in time. Okay? Now, so meron na tayo, nakasetup na tayo nakasetup na yung ating discretization. And then just let me introduce another notation. So we will denote by u sub ij yung temperature sa mga ating observation points and observation moments in time. So we will denote by u sub ij the temperature u of x sub I, comma, t sub j. Kasi ngayon, yung mga uijs na lamang ang ating makikeep track. Ito na lang yung masosolve natin, right? I going from, so si I goes from 0 to n plus 1, and j going from 0, yeah, subscripts na to, no? So this would be 0 to n plus 1. Ito yung mga subscripts ng ating temperature function. So ilang temperature values na lang yung malalaman natin? Sige nga. So pag pinasolve ko to sa computer, ilang temperature values na lang yung magkakaroon ako in the end. Dun sa homework example nyo, meron tayong isang function. Yung function u na yon, 10 e to the negative 40 sine 2x, siya yung temperature sa lahat ng x from 0 to pi sa lahat ng t greater than 0. So you will have infinitely many temperature values. Pero dito sa discretization na to, ilan na lamang yung temperature values na makukuha ko o magkaka-access tayo. Sige nga. Or masyado pang maaga para tanungin kayo ng mga ganun tanong. So ilang values ng uijs yung magkakaroon ako? Any guesses? Guys, andyan ba kayo? Okay, good. Nag-iisip. Sige, 30 seconds. M plus 1 J is higher. By the way, ito pala, no? Sanay na kayo na, case sensitive yung pinag-uusapan natin. Sa math kasi, yung little m, iba siya usually sa capital M na variable. Ano? So follow the proper cases. So ilan? Mas mataas dun sa hula ni Jace. Na m plus 1. So bilangin nyo lang, ilan yung uij's na posible? M plus 2, higher than that, Jace. Ayan, nakuha na ni Denmark. There would be a total of m plus 2 times n plus 2 temperature values. Alright? Kasi nga, dun sa space domain, yung ating rod na 0 to L ay hinati ko sa dapat equally spaced. Kunwari, equally spaced yan. Hinati ko sila sa capital M plus 2 points. At sabi ko, malalaman ko yung temperature sa mga M plus 2 points na yan, sa bawat isang M plus 2 points na yan at some time values. Tapos yung time, yung observation time na 0 to capital T, hinati ko naman into a total of capital N plus 2 moments in time. So ibig sabihin, ito yung idea. Kailangan ko makuha yung temperature dun sa bawat isang M plus 2 points na given. Alright? Dun sa discretization points na M plus 2, kailangan malaman ko yung temperature sa kanya sa lahat ng mga time samples natin. Halimbawa, T equals 0, alam ko dapat yung temperature sa bawat M plus 2 points. And that could be easy. That could be done without any computations or without any heavy computations because we have the initial condition for us. Okay? So alam natin yan. Then sa susunod na time step, halimbawa time t equals 0.1, kung ang ating delta t ay 0.1, malalaman ko uli ano yung temperature sa bawat M plus 2 points na to. Tapos sa susunod na time step t equals 0.2, malalaman ko yung temperature uli sa lahat ng M plus 2 points na ito. And meron akong capital N plus 2 na time steps. So ibig sabihin, alam ko yung temperature sa lahat ng M plus 2 points in space at N plus 2 moments in time. So I will have a total of M plus 2 times N plus 2 temperature values. Yun yung hahanapin natin. Alright? Pero essentially, alam ko na naman yung temperature value dito, temperature value dito. So I guess we'll just be looking for M times N kung hindi ako nagkakamali. Kasi alam na natin from the initial condition and the boundary conditions, ano yung temperature dun sa mga natitirang numbers. Alam natin yung temperature sa 0 at temperature sa L for all time steps. At alam natin yung temperature sa buong interval at time t equals 0. So medyo mababawasan ng konti yung M plus 2 times N plus 2. Alright? So yun yung idea. So meron na tayong target observation points and observation moments in time. Next question is, how do we discretize the differential equation? Kasi madali lang i-discretize yung conditions, right? Meron na tayong specific x's, meron na tayong specific t's. So kaya nating i-plug in yung mga specific x's at specific t's na yon dun sa boundary at initial conditions, makukuha na natin yung vector of values for these conditions. So okay na yun. Ang malaking problema, paano natin i-discretize itong differential operator na to? Okay? And for that, we'll be using a very familiar tool, the Taylor series expansion. Kaya lang, yung Taylor series expansion dito, medyo kakaiba. Kasi two variables to, pero ang gagawin lang naman natin, magka-Taylor series expansion ako along each variable. Bakit? Kasi tingnan nyo, meron lang tayong dalawang derivative na involved. Partial with respect to t, partial with respect to x. So kukunin ko yung Taylor series expansion ni u with respect to changes in x. That will be one approximation. And then an independent approximation will be the Taylor series expansion for u with respect to the variable t. So kahit na dalawa yung variables kay u and t, hindi naman nagsabay yung mga derivatives, luckily. Ito ay partial lang with respect to t. Ito ay order 2, pero dalawang derivatives lang to with respect to x. So dito sa right-hand side, treated as a constant si t. Dito sa left side, treated as a constant si x. So ibig sabihin, pwede akong magkaroon ng magkahiwalay na Taylor series expansion para sa kanila. So it's like taking the Taylor series expansion with respect only to a single variable. So I hope tandaan nyo pa yung Taylor series expansion mula sa 38. Ngayon natututunan nyo, hindi lang pala sila basta abstract conceptions. Ano? Napakalaking gamit nito, especially if you're doing applied math or you're doing numerical calculations. Ano? So let's do that. So let's use the Taylor series expansion. So let's see. Using the Taylor series expansion for, umpisa natin dun sa temporal as a space variable. So kunin ko yung Taylor series expansion para sa u of x plus delta x comma t. So sa space variable muna ako. Nagbabago si x pero constant si t. Alright? Tapos kukunin ko yung expansion nito about ito yung center of expansion, about the point x comma t. Alright? So space and temporal variable combo. Pag ginamit ko yung Taylor series expansion, tatanong ko sana, may gusto ba mag-recite ng Taylor series expansion? Medyo mahaba eh. Meron ba makapag-recite? Anyone who would like to recite? Ano yung Taylor series expansion ng u of x plus delta x comma t? Mahirap kasi ito pag ita-type eh. So kaya kung gusto niyo mag-recite, just raise your hand. Pero essentially, pag i-expand ko to, u of xt plus change in x, which is just delta x, times the derivative of u with respect to x evaluated at xt, all right, plus delta x quantity squared divided by 2 factorial times the second derivative with respect to x ng u of xt plus marami pang terms, right? It's an infinite summation, pero essentially ang format niya ay delta x to the power n divided by n factorial times the n partial derivative with respect to x of u. Right? So, yan yung Taylor series expansion. Hopefully, natandaan nyo na yung Taylor series expansion. Pero merong theorem na dun sa error term, dun sa Taylor series expansion, na yung error dito ay big O na lamang ni delta x cubed. Okay? So, para hindi na natin i-consider yung higher order terms. So, ang ibig sabihin lang nito, yung remainder term, yung mga, di ba, infinitely many pa, yung susunod na mga terms dun sa summation. But those infinitely many terms has a sum or has a magnitude that is a multiple of delta x cubed. Right? So, ibig sabihin, it is a constant times delta x quantity cubed. So sa big O notation, di na natin sinasama yung constant multiplier. Okay? So ibig sabihin, ang significant term dun sa mga tinanggal natin ay factor ni delta x cubed. Right? So meron pa ditong delta x to the fourth plus times a constant times delta x to the fifth times a constant. Pero yung mga higher powers ni delta x ay insignificant with respect to delta x cubed. So kaya yung pinaka-significant na term na lang yung iniiwan natin. Tapos hindi na natin iniisip yung constant multiplier. Basta isipin nyo ang significant contributor dun sa mga terms na tinanggal natin ay isang multiple ni delta x cubed. Alright? So yun yung big O notation. But I guess all of you have taken AMAT 152, so dapat alam nyo na yung Bachmann-Landau notations. So ito yung Taylor series expansion. Tapos, mula dito, okay, mako-compute ko kung, or makakuha ko ng approximation para kay partial of u with respect to x. Okay? So, siguro, I'll do the linear approximation. Kunin ko ba yung linear approximation? Sige. Yeah, I'll just do the algebra. Gusto kong i-solve ito. I'll solve for the partial of u with respect to x. Kasi nga, kailangan ko mamaya yung second partial. Tapos, kasi ganito rin yung gagawin ko sa time variable. Alright? So, tingnan natin yung pattern. para makuha ko yung approximation para kay partial of u with respect to x. Well, all I need to do is to isolate this to this side. So kailangan ko lang ilipat lahat ng terms dun sa kanan, sa kaliwa. Kailangan ko silang ilipat lahat, tapos i-divide by delta x. So what I'll get is the partial with respect to x ng uxt ay equals sa u of x plus delta x comma t minus u of xt, tapos magdi-divide ako ng delta x, right? So ito yon. Tapos ito nilipat ko sa kabila, tapos dinivide ko by delta x. Alright? Tapos meron pa to na minus delta x quantity squared over 2 factorial, then second partial with respect to x of uxt divided by delta x plus big O or minus big O ng delta x cubed over delta x. All right? So, yan yung mangyari. I just did the algebra, right? Pero tingnan nyo to, this will just be delta x cubed divided by delta x. So, magiging big O of delta x squared na lang to. Kasi originally, multiple siya ni delta x cubed. Pero dinivide ko siya by delta x. So, ito, magiging multiple na lang ni delta x squared. Tapos ito, may delta x ka dyan, meron kang delta x squared sa numerator, so it will just be delta x. And then what I'll do is I'll drop this term, kasi wala tayong access dito. Kasi hindi natin alam yung second partial derivative with respect to x. So we don't have any access to this, so I'll drop this and eventually get a degree 1 approximation to the partial derivative. Sabihin ko na lang, this is approximately equal to, or actually, wag approximately equal kagad. Ito ay equal sa this guy plus big O of delta x na lamang. Right? Bakit delta x na lamang? Kasi ito ay delta x squared and na-divide siya ng delta x sa ilalim. So essentially, this will be delta x all over 2 factorial. All right? And then, so pwede natin siyang tingnan as a multiple of delta x lamang. Right? Multiple siya ni delta x, tapos ito multiple ni delta x squared, is si delta x ay isang number na less than, which is very less than 1, right? Maliit dapat yung mga delta x na time steps natin. So kaya ibig sabihin yung malalaking powers ni delta x nag-approach sila ng 0. Right? So that's why yung malalaking powers ni delta x insignificant na sila kasi mas malalapit na sila kay 0. So essentially the driving force in these terms would be the one that is a multiple of delta x. And to keep track of that, gawin natin, sulat natin delta x. So meaning, this is an order 1 approximation to the partial derivative. Order 1 kasi ang error niya ay multiple lamang ni delta x. Okay? Now, this is something familiar. Tama ba? Kunin nyo lang kasi yung limit nito. As delta x approaches 0, you will get the partial of u with respect to x. All right? Usual derivative technique. Kaya gusto natin yung delta x dapat mag-approach ng 0. Okay? So essentially, this is our first order approximation to the derivative with respect to x. Okay? So basically, pwede nating sabihin na yung partial ni u with respect to x sub ij ay approximately equal kay u I plus 1, comma j minus u I sub j over delta x. Kasi para makuha yung partial derivative ni u at a particular number x sub I and a particular number t sub j, all right? So pag kinuha mo yung partial ni x, partial ni u with respect to x evaluated at x sub I, comma t sub j, all right? So ito yon, ito yung notation natin para doon. Ux kasi partial with respect to x, tapos kukunin natin yung value sa x sub I at t sub j. So ito ay magiging x sub I plus delta x. So basically, this would be x, this would be what? This would be I plus 1 delta x Kasi nga, ito yung forward sa space. Ito yung temperature at the same time value, pero dun sa katabi niyang x value, right? Forward. Minus uxitj. So uij lamang siya divided by delta x. Okay? Everything's good so far? Questions? Or nawala na ba kayo? Naiwan na ba kayo? Any questions, clarifications? Meron bang malabo? Questions? Everything making sense pa naman? Yan, dyan ako kinakabahan sa mga silence na yan eh. But hopefully you get the idea. Kasi ang point kung bakit ko to dinidiscuss in details. Kasi gusto ko makita nyo yung discretization process. Para ang gagawin nyo na lang, para sa final project, pwede kayong humanap ng isang ODE o isang PDE. Tapos i-apply nyo yung same methods na to para makagawa ng isang meaningful na inverse problem. Halimbawa, mag-search kayo sa internet, partial differential equations with applications. So halimbawa, bibigay niya sa inyo yung equation ng wave, bibigay niya sa inyo yung wave equation. Paano nagbe-behave say ang acoustic waves? Meron lang isa siyang PDE, tas may boundary at saka initial conditions. You apply the same thing we did here. Okay, medyo meron lang konting adjustments kasi iba na yung mga terms dun sa partial derivatives doon, pero the same principle will apply. So yun yung gusto kong makuha nyo from this one. Okay? Alright? Tapos similarly, pwede nyo gawin din yung parehas na bagay. Similarly, we can do the same thing for the time variable. Alright? So kapag ka naman kinuha nyo pag kinuha nyo yung Taylor series expansion ni u x comma t plus delta t, okay, about x comma t, you will get a similar expression. In fact, what you'll get is this guy. So makukuha niyo ang partial with respect to t ni u evaluated at x comma t ay equal lamang kay u of x t plus delta t, alright, minus u of x comma t all over delta t. Okay. So parang ito yung derivative with respect to time. Paano mo kukomputin yung derivative with respect to time ng temperature? Kunin mo yung temperature at the same point, pero dun sa susunod na time step. Minus yung temperature at the same point, pero at the current time, divided by delta t, which makes sense, right? Ganito natin kinocompute yung derivative. Yung function value sa susunod na step. Pero nasa parehas tayo na point na x, kukunin mo yung temperature niya one step into the future, minus yung temperature at the same point, at the current time, tapos i-divide ko yung difference by delta t. When delta t is very, very close to 0, this guy will be very, very close to the partial derivative of u with respect to t. Kaya pala to dapat ay approximation lang. Kung ayoko na approximation, gusto ko ay exactly equal, kailangan kong i-add yung big O term. Yung big O term dito ay linear approximation in delta t lamang. Okay? Tapos, hold on. So, okay, tingnan nyo to. Ito na yung partial ni u with respect to t, right? Pwede ko itong gamitin dito sa right-hand side ng ating PDE, right? So I can replace the right-hand side, the left-hand side of our PDE, the partial of u with respect to t, by this difference quotient. Okay? Ganun yung mangyayari talaga. So magiging discrete na siya. Kailangan ko lamang yung temperature at the particular point, tapos one step into the future in time, minus yung temperature currently divided by delta t. So naging discrete na yung left-hand side. So kailangan ko yung umisip, paano ko naman madi-discretize yung right-hand side? Pero ano ba yung itsura ng right-hand side? Oh, medyo komplikado. Ang right-hand side natin ay second partial derivative with respect to x ni u. So kailangan kong gumawa ng approximation para sa second derivative ni u with respect to time. Pero hindi na ako lalayo. Gagamitin ko yung Taylor series expansion pa rin. So let me just duplicate this one. Para dun sa second partial derivative. So let's write that down. Now, to discretize the partial derivative, the second partial derivative of u with respect to t, we make use of the following series expansion. So meron tayo nito. Kasi ang gagawin ko, kukunin ko yung expansion ngayon ni u, right? Pero ngayon sa x minus delta x. Okay? So ito ay forward formula. Kasi ang kinuha natin ay series expansion sa susunod na point, comma, t. Alright? Ngayon, kukunin ko yung backward formula. Kukunin ko naman yung function value ni u dun sa previous x value, x minus delta x. Alright? But essentially, yung expansion magiging kamukhang-kamukha pa rin, right? So this will be u of xt. But instead of delta x, ang increment ko ngayon minus delta x. So this will be minus delta x partial with respect to x ng uxt. And then this guy will still be plus delta x quantity squared. Kasi magkakaroon ako ng negative delta x quantity squared over 2 factorial. Pag sinimplify ko, magiging positive delta x squared na siya. Right? Divided by 2 factorial, partial with respect to x squared, second order partial with respect to x of uxt, tapos plus big O of delta x cubed din ito. Okay? Tapos, ang gagawin ko, i-add ko itong dalawa na to. So I'll have u of x plus delta x comma t plus u of x minus delta x comma t. Tingnan natin yung magiging sagot when I add these two guys. So in-add ko yung dalawang left-hand side, so I'm gonna add the two right-hand sides as well. So uxt plus uxt equals 2 u of x comma t. Delta x times partial with respect to x of u plus negative delta x partial of u with respect to x. So that's going to be 0. And then we'll have delta x squared over 2 factorial, second partial derivative, plus itself. So we'll get what? We'll get delta x quantity squared, second partial with respect to x ng uxt, plus we'll have big O of delta x cubed. So, Bachman lang daw arithmetic, right? Delta x cube, big O of delta x cube plus big O of delta x cube is still big O of delta x cube, right? Kasi parang ano to, multiple ni delta x cubed plus multiple ni delta x cubed, multiple pa rin ni delta x cubed, right? So, ganun yung arithmetic ng Bachman lang daw. Pero the goal here, remember, what's our goal? Our goal is to find a discretization for the second derivative of u with respect to x. So, ibig sabihin, ito yung sinusolve natin. Okay. Tapos, paano ko ito makukuha? Simple arithmetic na lang, no? I-isolate ko yung partial yung second partial ni u with respect to x to one side of the equation. So if I'll do that, we'll have what? We'll have partial with respect the second order partial derivative of u ay magiging equal kay u of x plus delta x comma t minus 2u x comma t plus u x minus delta x comma t all over delta x quantity squared, right? So ito, nilipat ko sa kaliwa. So kaya nagkaroon ng minus doon. Tapos dinivide ko both sides by delta x squared. Tama ba? Tama yung arithmetic ko. And then this would be plus big O ni delta x cubed. Pero then na-divide na siya by delta x squared. So multiple siya ni delta x cube, lilipat to sa kabila, right? So magiging negative big O ni delta x cube. Pero negative big O ni delta x cube ay equal sa positive big O ni delta x cube, right? So kasi multiples lang naman sila. Kaya lang, madidivide ng delta x squared na nanggaling dito. So ito ay big O na lamang ni delta x. So this is another first order approximation to the partial derivative. Pero parang kulang. Hold on. Dapat second order siya. I see. Dapat nga second order siya. Bakit second order? Kasi pag pinahaba ko yung expansion dito, magkakaroon ako ng minus, sorry. Kakaroon ng plus delta x cubed all over 3 factorial times third partial derivative. Tapos ito na yung big O ni delta x to the fourth. Okay. Tapos ito, magiging minus delta x cubed over 3 factorial, third partial derivative, uxt, plus a factor of delta x to the fourth. Okay? Tapos pag inad ko to at saka ito, magka-cancel yung third partial derivatives. So wala nga, dun sa sum, walang natitira na odd order derivative. Kasi nagka-cancel, right? Kasi meron kang positive at saka negative odd powers. So natitira lang ay yung mga even powers. So basically, I can think of it not as an order 3 approximation, but an order 4 approximation. Because anyway, the third order will just vanish to 0. Okay? So ito ay second order formula to. Nireconcile ko siya dun sa 174 kasi alam ko tong formula na to ay isang order 2 approximation para sa second derivative. And the nice thing about this is, okay, pwede ko na itong pampalit doon sa ating ODE, sa right-hand side ng ating PDE pala. So essentially, what we got here is that the second partial derivative with respect to x, okay? Ang notation natin, isa pa notation sa second partial derivative by u sub xx, right? Tapos kukunin ko yung value niya sa xitj. So ito siya. Para makuha ko yung value ng second derivative with respect to x at a particular x value x sub I and particular time value t sub j, annotation natin doon ay ito, right? Ito ay equal sa, sabi nung ating approximation ngayon, siya yung temperature at the current time, pero dun sa susunod na point, so it's gonna be u of I plus 1 comma j minus the temperature at the current time at the current point, so it's uij. Kasi nga, ito lang yun. Tapos, plus temperature at the previous point at the same time. So it's going to be u sub I minus 1 comma j all over delta x quantity squared. Gawin natin itong approximately equal. Okay? Now, using these things, so therefore, our PDE becomes this. The heat equation is approximated by the following finite difference equation. Finite difference equation. Finite difference siya kasi ano lang, meron tayong mga finite number of differences, all right? Meron lang tayong mga pinag-minus-minus na finite number and we get an approximation to the ODE. So basically, di ba, ang una natin ay d dt ng uxt, right? Pero alam na natin yung approximation sa first order derivative with respect to time. So it will just be u. So basically, ito yung mangyayari. Gusto natin ng u sub t at ij. Ay gusto ko maging equal sa d Tapos times second derivative xx ij for all I from 0 to n plus 1, m plus 1. And j going from 0 to n plus 1, right? Gusto natin itong mangyari, right? Kasi ngayon, hindi natin kayang i-match sa lahat ng x values at lahat ng t values kasi computers yung pagkakompute natin. So ngayon, gusto ko ngayon i-match na lamang yung, i-satisfy na lamang yung governing law dun sa ating discretization points. So gusto ko yung partial derivative ng mga values, alright, sa x sub I at t sub j ay maging equal dun sa constant d times the second partial derivative of u with respect to x dun sa mga xi at tj's na nandun sa ating discretization points. So finite na lamang yung bilang ng mga equations na gusto nating i-satisfy. Kaya lang hindi tayo tumigil dito kasi derivative pa rin to. It's a continuous operation which computers cannot do on their own, at least, or at least efficiently, right? Ganun din ito. Partial derivative with respect to u, hindi yan kayang i-manipulate ni computers. Kaya ang ginawa natin, nag-Taylor series expansion tayo, and we got an approximate para kay u sub tij. Remember, u sub tij, nasa na yon? Ito. Pwede ko siyang palitan nito. Ita-translate ko lamang siya dun sa ating subscript notation, right? So remember, it's gonna be the temperature at the same point, pero next time step. So one step into the future minus current temperature divided by delta T. So itong left-hand side ay partial derivative at the same x value, pero future time step minus current value, ij, all over delta t. Ito yung ating approximation dun sa left-hand side. And then para naman sa right-hand side, kakaroon tayo ng d, pero itong uxxij equal siya dito. Copy-paste ko na lang to. So we get this. Tapos, anong pwede natin pagsama-samahin dito? Yeah, so highlight ko na lang muna to. Inisip ko kung isosolve ko na. Abutin pa ba natin? Let's see. Gusto ko sanang ipakita kung bakit ito or kung bakit using this equations, tawagin nating star, kung bakit itong equation star na to ay sufficient na para ma-solve natin yung forward problem. Hold on. Tingnan natin. Okay, maybe to make things simpler, all right? So I will, because from here, I can multiply what? Yeah, I can multiply both sides by delta t. So I'll have ut I ng j plus 1 minus ut. Oops. Ang dami kasing parenthesis eh. U sub t ij ay equal kay d delta t over delta x squared. Okay? So minultiply ko both sides by delta t. Tapos nagkakaroon ng ui plus 1 j. Sorry. Mali yung nasa left side ko. Replay. Wala na tong partial derivative, no? Kasi ito nga pala si utij. So kailangan ko lang ay yung u sub, what? U sub I, comma j plus 1 minus u ij over delta t. Tama ba? Ito lang yung kailangan ko, no? Kasi nga, in-approximate natin yung partial with respect to t. Balikan natin. Yung partial with respect to t ay equal dito. So, ibig sabihin, ito ay ui, kaya lang one step into the future in time, minus uij over delta t. So, yun yung kailangan kong nandito. Yeah, wala na mga partial dito sa kabila. Napasobra ako ng partials kanina. Kaya pala, ang hirap niyang isulat. Dapat hindi ganun siya kahirap isulat. Ano? And then now I multiply both sides by delta t. So I'll have I'll have u sub I comma j plus 1 minus uij equals d delta t over delta x squared times ui plus 1j minus, pwede ko na pala siyang palaking parenthesis, u sub I plus 1j minus 2 ui sub j plus u sub I minus 1 comma j. Okay. So, and then we can let little d to be d delta t over delta x squared. Then, itong equation double star becomes what? So, I will isolate u sub I comma j plus 1 on the left-hand side. Okay? So, para, ito kasing isa-solve ko. Ano yung temperature sa lahat ng points in the x domain, pero in the next time step using previous values. Okay? So ito ay magiging d. So ito ay papalitan ko lang ng d. Tapos kopyahin ko itong buong ito. So u sub I plus 1j minus 2 u sub ij plus u I minus 1j plus uij. Yung uij nanggaling dun sa kabila. Transfer ko siya sa right-hand side. And then I can group my terms and I can have d times u sub I plus 1 comma j minus plus 1 minus 2d. Gawa nito. Tapos ito ay may 2 times d. Tapos ito ay may 1. Parehas kasi silang uij. I can just combine those terms. Times uij plus d times u sub I minus 1 j. Okay. So ito yung magiging basis equation natin. Let's call this equation dagger. Okay? So si equation dagger, siya yung gagawin natin para i-build up yung ating linear system when we do it next meeting na lang. Though yung MATLAB code ko para dun sa pag-solve ng forward problem ay nandun na sa canvas. Alright? So tingnan na lang natin kung paano siya makakatulong. Alright? So this equation dagger gives us what? So ibibigay niya sa atin yung temperature sa isang point x sub I at the next time step. Alright? Kasi nga nasa t sub j plus 1 na tayo. So makukompute natin yung temperature sa isang particular time x, sa isang particular point x sub I in the next time step using what? Using these values. Ano ba yung mga values na nasa kanan? Ito yung temperature dun sa katabi niyang point sa kanan kasi x sub a plus 1 pero sa time j. Plus, ito naman ay factor ng temperature sa sariling point pero at the current time. Right? Plus, ito naman yung temperature at the current time pero dun sa point na katabi niya. For instance, sige, let's say I equals 1 and j equals 1. So if I use this subscripts in equation dagger, we'll have u sub 1 comma 2 equals d ng u sub 2 comma 1 plus 1 minus 2d u sub 1 1 plus d u sub 0 comma 1. Okay? So, ibig sabihin, para makuha natin yung temperature kay x sub 1, x sub 0, this is x sub m plus 1, ito si x sub 1, ito si x sub 2, halimbawa time t equals 1. Alright. Para makuha yung temperature kay x sub 1, pero kay time 2, alright, kasi subscript nito ay 2, kailangan kong gamitin yung temperature dun sa katabi niyang point at the current time, which we can assume to be known, right? Plus 1 minus 2d times yung temperature dun sa point na yon, pero at the current time step, plus d times yung temperature dun sa katabi niyang point sa kaliwa, pero at the previous time. So these three temperature values, so puro temperature lang yan sa t equals 1, ano? Ibibigay niya sa atin yung temperature sa time t equals 2, right? Kaya lang kailangan natin yung temperature sa t equals 1 para mahanap yung temperature sa t equals 2. Pero malalaman ba natin yung temperature sa t equals sa temperature t equals 1? Kapag gusto natin yung temperature sa t equals 1, kakailanganin ko naman yung temperature sa t equals 0. Right? Kasi halimbawa, u of 1, comma 1 will be d of u 2, 0 plus 1 minus 2d u sub 1, 0 plus d u of 0, 0. Alright? Pero alam ko ba yung mga temperature values na yan at time t equals 0? Dapat. Saan manggagaling yung values at time t equals 0? Manggagaling yan dun sa ating, ang tawag natin dun? Manggagaling siya dun sa initial condition. Alright? Kasi yung initial condition, alam natin yung temperature u x sub 0. Alam natin yung temperature sa lahat ng x values at time t equals 0. So makakapagsimula tayo kasi alam natin yung temperature na ang subscript ay j equals 0. At alam ko yon sa lahat ng x's. Right? Tapos alam ko rin naman yung temperature dito sa kaliwa at dito sa kanan sa lahat ng time value. So ibig sabihin yung boundary at saka initial condition, they will get the ball rolling. Right? Sila yung magsisimula kasi kung makita nyo yung temperature at a particular point x sub I at a time step j plus 1 ay nakadepende sa temperature at the current time steps t sub j. So dapat alam mo yung value ng temperature sa t sub j sa lahat ng x's or at least sa tatlong x's. Yung point na hinahanapan mo ng temperature at the next time step, yung katabi niya sa kanan at yung katabi niya sa kaliwa. Now, to get the ball rolling, makikita natin next time when we try to write this into a code, importante yung previous values. Manggagaling tayo dun sa initial condition, which is the value of the temperature for all x's at time t equals 0. Tapos magagamit din natin yung value ng temperature at the left and the right endpoints kasi para ma-compute yung temperature kay x1 at the next time step, kailangan ko yung temperature kay x sub 0 at the current time step. Alright? So, kailangan ko yung sa kapitbahay. So, kailangan alam ko to. Pero no problem about that because we already know what the temperature at x sub 0 sa lahat ng time value. Okay? Para naman sa temperature ni x sub m na nandito, kakailanganin ko yung temperature kay x sub m plus 1. Pero no problem about that because we already know what the temperature is at the right boundary from the boundary conditions. Tapos para ma-compute yung temperature sa t equals 1 sa lahat ng x's, kailangan ko namang malaman ano yung temperature initially sa time t equals 0, but that's okay because that is given by the initial condition. So parang isa siyang malaking domino effect. So ma-observe, ma-predict natin yung temperature in the next time step using the temperature at the current time step ng mga magkakatabi na points. Okay? And we will go back here and try to write the code for this one on Friday. On Tuesday. Sorry. Mali-mali na yung dates ko. On Thursday, all right? But I already uploaded the MATLAB code that I wrote for this problem. So, pwede nyo siyang i-download, pwede nyo siyang tingnan, and then let's discuss it on Thursday. Okay? But for now, are there any questions, clarifications? So yan, meron kayong isang numerical technique na natutunan, ano? Ito yung pagsasolve ng partial differential equations numerically. Any questions, clarifications? Wala? Sure? Okay, sige, hindi ko na kayo pipilitin. So probably you're still digesting things, or you want to rewatch the recording to go back to go back to those parts that you didn't appreciate too much today. So that's fine. Ito yung kagandahan ng online setup, ano. Pwede niyong balikan yung recording. Kung medyo may malabong part tas nahiya kayo na itanong, I don't know kung bakit nahihiyang magtanong, ano. So pwede niyong balikan yung recording and then replay it over and over again, or bagalan or pabilisan siya. Tapos let me know lang if you have some questions, because your understanding of this is crucial para dun sa pagbuo nyo ng final project. Kasi nga, ito yung pwede nyo gawin eh. Pag naintindihan nyo itong ginawa natin dito today, pwede nyo gawin para sa final project. Hanap na lang ako ng isang PDE o isang ODE na say nagsosolve ng nagmo-model sa isang actual phenomenon. Hindi niyo na kailangan maintindihan yung theory behind that PDE. Basta makuha niyo lang yung PDE model at ma-appreciate niyo ano yung minomodel ng PDE na yon. Ba nakita niyo wave equation, ganito lang to, mga partial derivatives lang din to, kamukhang-kamukha ng ginawa namin sa heat equation. So tapos titingnan ko, interesting yung application niya, it piqued my interest. So ang gagawin ko, i-discretize ko siya in the same manner that we did today. Tapos, pwede nyo nang gawin, i-pattern yung gagawin yung project dun sa gagawin natin in the next few meetings. Alright? So I hope this gave you some idea of what to do. Okay? Now, dahil ina-absorb nyo pa, I hope you get these things. If not, I really hope you have some questions for me. You can send me an email, a chat, or just bring them up on Thursday, alright? Kasi sa Thursday, ang plano ko, mag-review ng kaunti nito, tapos isulat na siya into a matrix form, tapos ita-translate natin siya into a MATLAB code. Alright? So with that, let's call it a day now. Thank you guys for joining me today. Enjoy the rest of the day. Keep safe, and let's see each other on Thursday. Okay? Pero don't forget, meron tayong homework, right? So yung pag-verify ng solution dun sa forward problem, the analytic way, due, I think, on Friday. So, pero madali lang siya. May 4 na nga nakapag-submit as of kaninang madaling araw na checkan ko na rin. So, you can submit it as soon as you have, alright? Bye, guys!